No, this is
We did
divide.
like regular division, now we're doing division kind of as well. We had a program that was just division.
So now we're going to be caught. Oh, separate.
This is defining as a subroutine, so you have to figure out how to get the parameters and how to return values in a standardized way. Yep, go ahead.
You are correct though, we had division just in main.
Is there any like special trick you could use to compare the pointer to the remainder? I think that third parameter, is there like a special trick to compare it with 0? Because like how my program does it, like after the actual division is done, like the repeated subtraction, I have the remainder, the quotient, the divisor, and the stack pointer, right? So I get rid of the divisor since you don't need that, and I put the remainder. I put the pointer to remainder there.
Okay.
But then you'll have to compare that with 0. So you have to, well, like there's no other register you can use to load 0. So you have to put it onto the
Okay,
stack.
so that's a good question. So the question is, okay, so I'm going to start the lecture now. So the question is, what do you do when you run out of registers and you need to do something? Okay,
Local
because
variables.
sorry?
Do we have to use local variables?
Well, okay, so it depends on how you want to look at it. You can look at it as local variables, but you can also look at it as just some space on the stack, okay? Now, in C and C++ programming, you have no concept of registers, so there's no such limitation as, oh, I just use up all 4 registers. But in assembly language programming, yes, we only have 4 registers. We would love to keep everything in the registers because that way we can do all the computation, we can do all the compare, get things done. But you only got so many registers. Even if I give you 32 registers, at some point you're going to run out. So now the question is, okay, I just ran out of registers. What am I going to do? Okay. So let's use that as a starting point of this particular lecture. So we'll try to do something that is relatively complex that will make us run out of registers. Okay? Okay? So let's go ahead and run out of registers. Do something that will run out of registers. String and compare probably will do it. Okay? Because we need to do the counting. We also need the 2 registers for the dereferencing of the pointers and stuff like that. So what are we going to do when we are running out of registers? All right, so we'll do that. You guys saw how quickly I just came up with an idea and go like, yeah, let's go do this. It's fun. Okay. So we'll do string and compare, string and CMP. And if you don't know what is string and compare, you can always find the man page, which describes exactly what we are dealing with, string and CMP, which has the same web page or the same man page as string compare. So in this case, string and compare has 1 extra parameter to the end, which is n, which is the maximum number of bytes we should be comparing. If we do not find the end of the strings before n, then we just conclude with whatever last character it is that we have seen. Okay, so return value is basically the same thing. If the first string is less than the second string, we return a negative value. If it's greater than, we return a positive value. If they're the same, return 0. So the only difference is in string and compare, it compares only the first n bytes of the strings. Okay. So getting back here, we'll just write the subroutine in C first, and then we'll convert it into assembly. And I'm pretty sure this time we won't have enough registers because of n being a counter. Okay, so writing this in C is fairly easy because we just have to, because we don't have any limitations of registers. So in this case, we can say as long as, okay, so we can use n as a limiting factor first. So as long as n is not 0, and whatever S1 points to is the same as whatever S2 points to, and at least one of these 2 is non-null, because if one is null, the other one is null as well at this point. So this becomes the condition of the loop, and in the loop here, we just increment everything and decrement n by 1. So we say increment S1, increment S2, and then we decrement n. That's all we're going to do in the loop. When we get out of the loop, okay, it's time to do some quick analysis of, okay, how do we get out of this loop? We can get out of this loop when n equals to 0, which means, okay, we just ran out of bytes to compare. We can also get out of the loop when whatever S1 points to is different from whatever S2 points to, because we just found the first byte of difference between the two strings. It's time to get out. Or we can also get out when both strings have hit the end, which is the null character, which means star S1, which is the last condition of the conjunction, is false. Those are the conditions to get out. Whatever reason we get out, we just have to return the same value as the other one, the string compare case. So we just say return, yep, go ahead.
You said it could be, for the third portion of the while loop, you said that could be S2 as well, correct? It's either of them?
They will be the same at this point.
Okay.
Because in order to evaluate the third condition of a conjunction, it means the first two conjunctions have to be true. Because with conjunctions, the order of evaluation is guaranteed left to right. And then we use lazy evaluation, which means if the first two are not true, both true, we won't even bother with the third one. So if the first two conditions are true, it means n is non-zero. It also means whatever S1 points to is the same thing as whatever S2 points to.
So they would both, okay.
They are the same already, so I'm just really asking, are they both null or are they both non-null? If they're both non-null, keep going, because we haven't hit the end of the strings yet. But if at least one of them is a null, the other one is guaranteed to be a null, which means we have hit the end of string for both strings, and it's time to get out. So this is the actual C code, and now we've tried to implement it in assembly, and we'll try to keep things in registers as much as possible. Okay, which is basically the idea of, we don't have enough registers. Okay, so you can also see in this case we don't have any local variables. Okay, S1 is just a parameter, S2 is just a parameter, and it's just a parameter. So that gives you a clue of you can actually modify your parameters. Okay? All right, so we'll go ahead and implement this in assembly. Okay, so to implement the whole thing in assembly, I'm going to comment out every single line of code. Could have done this in VI and have one single command to do it. strncmp, and we want to know what is on the stack. So on the stack, we'll have n first. It is the last parameter, which is pushed first, and therefore it has the highest address. S2 is the next one. S1 is the first parameter. It is pushed last, and therefore it has the lowest memory location. And then we have the return address, and this is the very last thing pushed on the stack by the caller, and as a result, the stack pointer, which is our register D, points to it at the entry point of string compare. Okay, so we now first have to implement this while condition. So with any type of while condition, we know that we have to come back to it at some point. There's an end to it. And also we know that we have to get back to the beginning unconditionally when we get to the end, or get to the end of the body. We have to get back to the beginning. And it is also a good idea to put this here, so that here we just specify, okay, when do we get out of this? Okay, so to get out of this, we get out when any one of the condition is false, but we have to evaluate it in this specific order. So the first one is to say, okay, when n is 0, we get out. So now the question is, do you want to keep as many things in registers as possible? Okay, and the answer is obvious. Okay, yes, we do, because that can help make things go faster. So let's say we want to keep n in the register. Okay, I'm going to write down here. Okay, try to keep n in a register. Okay, so to do that, it means before the loop we have to initialize a particular variable with n. And we'll see which one we want to use. Let's use C for that purpose. Okay. Register C. Okay. So we have to initialize register C first so that it is n. So CPR CD C points to the return address. We have to increment it a few times. Once, it is now S1, now it's S2, now it is N, and then we do LD C, C. C is N at this point. Is that okay? What about the pointers? We also want to put those in registers. Now, but now we have a, yeah, go
Are you
ahead.
recording?
I believe so. Yep, it's on, and the voice is good too. So it's good to check. It's good to check. Okay, but at this point, we kind of know that we definitely don't have enough registers, because so we'll see what we can do here. So we'll try to make that assumption that register C is the counter. That's why I use N for that, because C stands for counter. Okay, so we'll say, okay, we just want to compare C to 0 in this case. So we say LDI, we pick one of the other registers. So we pick on register A because we know register A is really, disposable. So we say, let's compare these two. Okay, C and C. First, register C versus register A. And if they are the same, which means it is null, we get out. Okay, so we go to while end in this case, done. Okay, so now we have to compare whatever S2 points to whatever S1 points to. Well, it's going to be a big hassle because we are not keeping these two in registers. So now we have to say, okay, we can always try our best so that we don't use up register C. So we'll see whether we can do that or not. So we'll load register B with D, so that, okay. Now you might want to do this for every single line, because it really helps you to kind of visualize and understand how the stack is organized in terms of the parameters. So we increment B once, it becomes S2, which is kind of what I want. Okay, that's good. So we want to do LDBB. Okay, so I'm gonna comment here. B is now pointing to the S2. B is S2. Okay, can everybody see the difference between these two lines? After the increment, B is pointing to S2, which means it is the address of S2. But if I load indirect, B is the parameter S2. But that's not what I want. Yep, go ahead.
What did it point to S1?
Huh?
Because you copy D and then you increment.
Oh, we need one more increment. Thank you.
Okay.
Thank you.
Yeah.
There we go. Thank you. All right, so then we do it one more time. Right? Which is what we want to compare. Yep, because we're comparing what S2 points to. And then we do the same thing, CPR AD. So we can probably, in fact, not use C at all. But this may be telling you something about the way you use your code. If you keep everything in the parameters and not keep those in registers, you won't be running out of registers. But we'll check this out. We'll finish this program. Okay, so at this point, A points to the return address. Increment A points to S1. Load A indirect A. So the A is S1. And then do it one more time. So the A is whatever S1 points to. So now we can compare those two, A, B. But this time we want to continue execution, JZI. If they're the same, that's continuing the loop, okay? So we'll say check the reference S1. Otherwise, we jump to the end of the subroutine, while end. This is check the reference S1. So we still have register A containing whatever S1 points to, which means we can just load IB with 0 now. And then we say CMP AB JZI. If they are the same, if it is 0, we want to get out of the loop. So while end is where we want to go. And now we get into the body of the loop. Okay, in the body of the loop, register C still has the counter, so we can decrement C. And then we can do the other two, which is incrementing S2 and S1. So now we have to go through all the trouble and do it all over again. Increment B, LD. Okay, this is where things, okay. I still have enough registers to play with it, so I'm not sure whether we want to do it this way or not. Okay. Yep, we still have enough registers. And then we can increment B one more time. LD AB. Increment A. STDA. And then unconditionally branch back. Okay, so this stuff here goes here. There we go. So I didn't quite create a case where I run out of registers, but if you do run out of registers, this is a trick you can do. Okay, so I'll finish this program later, but I'm just going to show you the trick. Okay, if we run out of registers, you can always save the registers onto the stack without destroying anything else. Let me say that one more time. This is really important. You can always save the register on the stack without destroying any other register, which means we can do something like this. We can say decrement D, but doesn't that destroy the stack pointer? But that's okay, because as long as you know how to balance the stack pointer later on, you can always recover the stack pointer to exactly the same place that it is. Okay, so you use decrement and then you std whatever register. Okay, so let's say we want to be able to use registers A, B, and C. So what you do is you store all three. Okay, decrement D, std B, decrement D, std C. Okay, so now we can use registers A, B, and C any way we want to. Okay, but keep in mind that 3 more bytes are pushed on stack, which also means if you need to go back to one of the parameters, they're no longer the distance that we know before, because the distance that we knew before is based on the assumption that the stack pointer points to the return address. Now it is pointing to 3 bytes below what we expect it to be, which also means just the calculation is going to be off. When it's time to, when it is time to resume the values of A, B, and C, do the following. It's exactly the opposite order. Okay, you do LDC D, increment D, LDBD, increment D, LDA D, increment D.
But
Yep.
if you've incremented, now those disappeared, right? Because they're below the pointer, so they could have something
Correct.
else in them. Okay.
Yep. Which is okay, because the whole purpose is to save the registers so that we can use registers A, B, and C for whatever purpose. When we are done with that, now we restore the 3 registers back so that we can now continue whatever we we can continue the assumption that registers A, B, and C have whatever they had before. Yep, go ahead.
Why would they have something else in them once we increment the pointer? Because we haven't done anything to those memory values.
Yes, it's a,
That is correct. Okay, that's a very good question. Let me repeat the question because the mic doesn't pick you up as well. So the question is, when you move the stack pointer below, why would the content disappear? Because nothing else should be going on. That is absolutely correct when you're dealing with the toy processor, which doesn't have the ability of dealing with interrupts. So, but since the question was asked, and this is probably the right point, to kind of answer the question, I'm going to answer the question. And interrupts is basically one of the concepts that we have to talk about anyway in this class. It's just that the toy processor doesn't have an interrupt ability. So we'll go ahead and explain that. Maybe at some point I'll add the ability to interrupt with the toy processor, but not this semester. Maybe I should version the toy processor using a semester. Which version are we using? It's F17 or Spring 18. Okay. All right. So let me switch back to the camera. Autofocus. Kind of focused. Okay. All right. So this is the concept of interrupts. Okay, that's the concept that we are talking about. It's just kind of a small digression from what we are talking about, but it does definitely relates to how we use the stack. Okay. So the question now is, so this is the stack. Okay. This is high memory address. This is low memory address. This is the usual way that I display memory or write memory in a graphical way. And let's say this is where the stack pointer points to. Okay. In our case, it is register D. So the idea is anything that is below the stack pointer, like this portion here, we really don't know what is going on with this memory. Okay, they can be overwritten without your program, your code, knowing anything about it. Then you go like, how? That is not possible because there's no way we can actually continue execution at some other place other than what we have planned for the program. That is 100% true for the toy processor. But for a real processor, it has a mechanism called interrupts, and that mechanism can destroy stuff that is below what you know as the current value of the stack pointer. Okay, so this digression talks about what an interrupt is and why you cannot make the assumption that memory below the stack pointer will remain intact in many cases. Okay. So to talk about interrupts, the best way to talk about it is to talk about polling first. Okay. So polling, P-O-L-L-I-N-G, is a technique of how a processor can interact with an input-output device. What input-output device are we talking about? Well, typically the keyboard. Okay. So even if you go all the way back to the original IBM PC, it still has a keyboard. Okay, it may not even have a mouse, but it has a keyboard. So the question is, how does DOS, okay, the original operating system for PCs, how does DOS know that you just type CD, C, D, press the enter key? Okay. Well, the keyboard connects with a physical wire, right? And the processor or the motherboard in the computer can receive the signal coming from the keyboard controller, and they go like, oh, you just press a particular key. Oh, you just depress a particular key. In other words, from the hardware perspective, your PC doesn't really know what character you have typed. It just knows it only knows of the event of you pressing on the key and depressing a particular key.
but it knows which key it is, right?
It knows which
Has
key
an
it
address
is.
kind of, or?
Yeah, it knows the key because it has the row and the column kind of thing. So what it does is, on the keyboard itself, it has its own controller, which is a very tiny, small processor. And what it does is it will continuously scan and go like, okay, I'm putting a voltage on the first row of all the keys, and then it will sense, the columns, which one is detecting the high voltage. Then that way it knows, okay, this particular key and that particular key are pressed. So you can press multiple keys, and it will still be able to detect it. And then it will move on to the second row, put a high voltage on the second row, but take the voltage away from the first row, and then it will do the same thing. It will try to detect which column is detecting the high voltage, and so it can detect basically the entire map of all the keys and find out what key is being pressed at a particular time. But that information is sent back to your motherboard, to the motherboard in a serial way. Okay, it's just saying, okay, this particular key is pressed, that particular key is depressed, and so on. Okay, is that okay so far? All right. So now, from the perspective of writing that software, DOS, okay, or the foundation of DOS on the PC, how do you know that the key is pressed? Yep.
With the USB interface, the processor checks.
How does it check?
It looks, I would assume it would look for a memory address or something.
Yep. But there are specialized instructions to do it. So, but what are we doing? What we're doing with polling is we're asking this question: as long as not key pressed, stay in this busy loop. In other words, now how this is implemented is not really that important, okay? Because how key press is implemented depends on hardware. Okay, which idle registers are you asking? Okay, is there a key press on the keyboard? Is there a key press on the keyboard? Is there a key press on the keyboard? Okay. When you're dealing with DOS, this is okay, because how many users can be on a particular old PC, the original PC, at any particular time? One user. How many things can that one user be doing at any particular time on that computer? One thing, okay? Which means if your entire computer is locked up by just asking that question over and over again, it's okay, because there's nothing else going on. Is that okay? So let's say you press a key. You press a key, and then this function will return true. The negation of true is false. Then this loop exits, and then whatever goes after this will probably have something to do with like getting the key code, interpreting what character is corresponding to that key code. It will ask whether the caps lock status is on or off. It will ask whether the shift key is still depressed in order to understand whether it's an uppercase or lowercase letter. Okay, so it will do all the other processing after this. But the idea is this is polling. This whole thing is polling. We don't like to do polling because we like to multitask. Okay, so to use an example of my office hours, okay, this will be equivalent to me asking, is there someone waiting outside? No. Is there someone waiting outside? And I keep asking that question continuously for the entire office hour. I'm not going to do that. Okay, I would much rather either doze off, okay, put myself into the energy saving state, right? Or I would, check my email, do something else, have lunch, that sort of thing, right? So I would like to do something else if nobody is waiting outside who wants to, have questions. So this is not efficient, okay? It can be done. It doesn't need a whole lot of stuff, but it is not efficient. So what's going to happen next is we have the mechanism of interrupts. Okay, so interrupts is implemented in actual hardware. So when you look at the CPU, or these days we just call it the processor, it doesn't really matter which term you use, there's one line, at least one line, that is called the interrupt line. Okay, it's usually a slashed interrupt line, which means it is active low, which means usually it is high, but when there's something going on, it needs to be asserted, and when it is asserted, it has a low voltage. Okay, this is what we call active low. In this case, this interrupt line, let's just say that the only concern we have is the keyboard controller. So the keyboard controller now connects to the CPU. It has one connection called the interrupt, okay, which is normally high. Okay, normally it says nothing is going on. But when I press a key on the keyboard controller will now say, there's a key. Well, CPU, you need to do some processing here. So what will happen is the keyboard controller will turn the interrupt line into a 0, in which case the processor will now say, okay, hold on a second, let me finish the current instruction, and then it will pay attention to the interrupt. Okay? It's equivalent to me, somebody is standing at my door, knock on the door, that's the interrupt. Okay? So instead of saying, okay, come in and ask me questions, I'm going to say, okay, let me finish what I'm doing. Okay, let me finish the atomic operation that I'm performing. Atomic in this case has nothing to do with nuclear. It has to do with indivisible. Okay, I have to finish the one thing, the one instruction that I'm executing, and then I'll go like, okay, now I'm ready to surface the interrupt. Surfacing the interrupt in this case is really just having a conversation with the keyboard controller and say, what key is pressed? Oh, this key is pressed, and so on. Yep, go ahead.
You've probably witnessed when you're doing something on the computer and something loads while you're typing and it takes a second for the words to display on the screen. Is that what's happening? There's a delay.
If it is a delay that you can see, it is because the process is really busy doing something else. Okay, but the interrupt process is basically saying, okay, so what goes on is, this is the first event. Okay, the keyboard controller says, I need your attention, CPU. Then the CPU will go ask, okay, tell me what is the key being pressed or what is happening. And then the keyboard controller will return and say, oh, that's the key being pressed. This is the key code. Okay. But in order for the processor to do this, it needs to have the software to do it. Okay? In other words, the processor itself doesn't innately know how to handle the keyboard saying, okay, we got a key event here. It needs to run some code to do it. Okay? So now you can kind of imagine in your program. Okay? So this is tax program. So tax code is executing just fine. Okay? At some point, event 1 happens. Okay, so at this point, I'm going to use the same label. Event 1 happens. And this is kind of like halfway through my code. Then the processor says, okay, I know this is coming from the keyboard controller. There is a particular subroutine sitting somewhere in the memory that I need to execute. I'm going to use green to represent that code. So green here is, it belongs to the same memory space, but it's a different program, different subroutine. So this is what we call an ISR. ISR stands for interrupt surface routine. Okay, it's just your code that says, okay, this is how you handle a key press event. Okay, all right. So we have a transition. So 1 will transition this execution of code to the beginning of this ISR. The ISR will, basically do number 2. It will do number 3, and then at some point that's going to be, it will conclude. Okay, this comes to a conclusion and go like, okay, I'm done handling the keyboard. We store that key press into a buffer so that later on tax program can try to read it and go like, oh, okay, I see somebody press a key. This is what I want to do with that key press. Okay, but at this point, it will resume execution. I'm going to use red again to where it left off in my program, so that my program can now continue its execution. Okay, is this picture okay so far? Of the event that is actually happening in terms of hardware, and also how that corresponds to the flow of execution of my opcode in RAM. Okay, so far so good. So now we got a question. the green arrow, okay, let me point out which arrow we are talking about. The green arrow is not a problem. Okay, going from my code to the ISR is not a problem. Because you can kind of imagine that each I/O device kind of have its own interrupt line. So when your SATA controller says, hey, I need your attention because I just transfer all the data onto the disk, is there anything else to do? It has its own interrupt line. The processor knows who is interrupting and where the ISR is corresponding to that interrupt. So you can kind of make that assumption already. So the green arrow is not an issue. The red arrow coming back is an issue. How does the ISR know where to go back to resume execution in my code? That is a question. That is a problem. What do you think the answer is? And why it relates to the question that you guys asked a little bit earlier of, hey, how come stuff that is below the stack pointer may get corrupted? So our issue is with this red line here. The line that goes from the ISR at the end of the ISR, the interrupt surface routine, getting back to the resuming point of my code. How does it know where to go back to? It goes on the stack, exactly. It is just like a call, except it is not done by opcodes. It is done by the hardware. Okay?
Stores it right.
Exactly. Because I have no control over where the green line happens. The green line can happen over here in my code. It can happen here in my code. I have no idea. This is an asynchronous event. The green line is representing an asynchronous event, which means from the software perspective, it has absolutely no idea when it is going to happen. Okay? So I cannot prepare for that. I can only do my best and say I'm just executing my code. Okay? When the hardware interrupt happens, my code doesn't know anything about it. Okay? The processor in hardware is taking care of the transition from my code to the ISR, to the interrupt surface routine. The green arrow is implemented 100% in hardware.
But it doesn't do it in such a way that it leaves the stack how it was when it
does
started.
leave the stack. So the hardware, the processor, when it handles this, is going to push a return address onto the stack.
Mm-hmm.
That's why, but do you know about that, the green transition, the green arrow transition? Your code doesn't know it.
Mm-hmm.
So would your code also anticipate and go like, oh, somebody's going to use up that byte that is below what the stack point is pointing to?
Mm-hmm.
No, your code doesn't know that either. So the only assumption you can make is things can happen to any byte below where the stack pointer is pointing to, because the green arrow that is being pointed to right now is equivalent to a call. What is in the process of a call? Okay, so I'm going to use blue color to document this transition here. It is implemented in hardware, not using opcodes, but it has the equivalent effect of decrementing D, LDI, some register with ISR address. Oops, I take it back, sorry. Whatever point it is interrupting. So it's basically the program counter. It's just copying the program counter to, okay, take this back. It's STD with whatever the program counter has. Now, we cannot write that code. That opcode does not exist, but what the blue line is, what the blue stuff is saying is it is equivalent to doing that, but in the processor itself.
So are we saying the ISR, it does access the stack, but then it doesn't increment, decrement properly? Or is it just like while it's doing that? Oh, okay, but while it's doing that, it could just mess up what's already on there?
Yeah, exactly.
Okay.
So when the ISR executes, it can use the stack as if your code is using the stack.
Okay.
As long as the ISR keeps the stack pointer balanced, it's all good.
Okay, so when it goes back to tax code right there, it'll be at the same spot, but it could have messed up stuff below and above it.
It could
Or-
just below.
Oh, okay.
Not above. So whatever the stack point is pointing to and whatever is above it is safe. That is your stuff. But any location below what the stack point is pointing to is quote unquote available. And the ISR makes that assumption. You go like, okay, I'm not gonna mess up anything above where the return address is pointing to, when its own return address is, but whatever is below is free, is available.
Gotcha.
Is that okay?
Yeah.
So this is why, in general, not the toy processor, but in general, you cannot assume locations below the stack pointer, where the stack pointer is pointing to, can preserve the values. You basically have to make the assumption of if it's below what the stack pointer is pointing to, that content can change without your code noticing.
So don't count on it being there.
Do not count on it.
Yeah.
Yep.
Cool.
And that is also the reason why we decrement the stack pointer first before we store. Because if you store first, then you can potentially cause a problem. Whatever you store can disappear. But if you allocate first by decrementing the stack pointer, you basically say, don't touch this.
Okay.
If at that point interrupt happens, it's still okay. Okay, nobody's going to touch that location that you just reserved. And then when the ISR returns, you can now go back and you fill that location with whatever content you want. Is this okay? It is kind of abstract because there are many things going on at the same time. Yep, go ahead.
Is the program counter in a real processor tracked in its own register?
Yes.
Okay.
So that's a good question. So the question is the processor program counter its own register? So to answer the question, I keep using the wrong one, because the first one is C. So we want 1998 with a tilde symbol. So when you look at the processor, the program counter is definitely its own register. It's just that the current way of the toy processor does not have the ability to handle interrupts. Because what it means is when you have an interrupt, the program the processor has to go to a specific location in the microcode ROM that does not actually correspond to an opcode, and it has to execute some code over there to figure out where to continue execution. Has to be pretty much a fixed place or pre-programmed space. Yep. And this is also why in most processor they have a quote-unquote software interrupt instruction, because that instruction is just a software way of triggering exactly the same mechanism as if a hardware interrupt just happened. Yep, go ahead.
Kind of unrelated. The reason we're using your toy processor is so we can track what happens.
Exactly. The reason why I want to use the toy processor in this class is the transparency of the entire thing. So that when you ask, how did the LD instruction execute? What does it do in order to, let's say we have LD, comma, and then in parentheses D. Okay. How did it get it done? Well, all you have to do is to look up the microcode corresponding to LDAD, right? And then you look at how it exercises the multiplexers and demultiplexers to establish the path between RAM and register A. That is the whole reason why we use a toy processor, because this explains how opcodes execute much better than I can possibly explain, because this is the actual mechanism. Instead of using poetry to describe a scenery, I took a picture.
Yeah. Yeah.
Or better yet, we have a field trip. I just say, okay, let's go.
Yeah.
Put you guys over there at the spot.
And my other question is, if we were actually using assembly, but if we weren't using the toy processor, we'd be using the processor on the computer itself?
Correct. Now,
Can we do
so
irreparable damage to the processor? through
no,
assembly?
you cannot.
Okay.
Okay. So, all right. So that's a very good question. So let me repeat the question so that the microphone picks it up.
All right.
So the question is, if we're not using the toy processor and using the actual processor, in the PC or in your cell phone, can we do, irreversible damage to? Okay, I'm assuming you're talking about hardware damage and not just crashing the system.
Yeah.
Okay, the answer is if it is properly designed, you should not be able to.
So it could be poorly made processor.
If it's poorly engineered, then yes, the answer is you can potentially cause problems. To understand that one, you can actually look up on the internet and find some examples of a poorly designed architecture, and I think the Pentium 4 with Linux compiling can cause issues. It could be. It may not be the Pentium 4, but it's one of the earlier 32-bit architectures. So basically, what happens is it only has one single integer ALU, and there's not sufficient heat extraction from that portion of the processor. When you're using Windows doesn't use certain type of ALU operations as intensely as the compiling of the Linux kernel. So when Intel tests the processor using Windows, using DOS or whatever at the time, it ran fine because that particular point of the processor was used kind of in a way that is used like, let's say 60% duty cycle, so it's not overly exercised. So heat extraction was not an issue.
Yep. Just curious, around when did the Pentium 4 come out?
I cannot remember. So let me.
Late 90s, early 2000s, or?
Pentium 4 came out after I moved, so it's after 2001 for sure.
Oh, for sure. I was
Yeah.
curious.
So Intel Linux compiling overheat. Nope.
Intel power plant.
Yep, go ahead.
Why does Linux rely on ALU processing more than Windows does?
It has to do with the optimizer. The compiler, has an optimizer, and whatever you do with the optimizer exercises instructions in a particular way that will overheat a particular component in the Intel processor. I cannot remember exactly which Intel processor. I was trying to look it up, but it was one of those things where a typical Windows test platform would not review the problem. But when you compile the Linux kernel, then it will actually overheat it. So when you overheat a component in the processor enough times, that can actually cause damage. Not so much explosion.
No, you let out the magic smoke.
Not so much explosion, but it will speed up the migration of what we call the impurity or the dope, in silicon. And when that stuff migrates, more than they should, then the processor will fail to operate. So unless a processor is designed incorrectly or it is not well engineered, typically software cannot damage hardware. Yep.
Did they later update the compiler so it wasn't so ALU dependent, or did they just say screw that architecture, we'll wait to the next one?
They just waited for the next one. Yep. I cannot remember which one, but it definitely had to do with compiling the Linux kernel.
Dangers of using Linux.
Crashing. I cannot remember which one, but it was one of the Intel processors. You guys can probably dig it up a little bit more. When we have more time, we can do it. Okay, so getting back to that picture. So are there any questions about this one? Any questions? Okay, so you might go to another class. Okay, so let's say we're talking about the same class, but taught at Sacramento City College, because they're still using the x86 instruction set over there. Okay, they're using the Intel processor line, they're using the Intel processor instructions, and so on and so forth. And you ask students in that class and go like, okay, if you don't follow these rules, okay, that you always allocate the space by decrementing the stack pointer first before using it, have you ever experienced, the stack content just, getting clobbered, okay? And they will tell you no. And you go like, okay, so Tech just lied. Well, I did not lie, technically. I did not tell you the entire truth. There's a difference. So what I did not tell you is all modern processors have a protected mode of operation. Okay? What that means is your thread, whatever program you're executing, whatever thread of whatever process that you're executing has its own stack. When interrupt happens, it does not use your stack. When interrupt happens, it will switch to the system stack, the kernel stack, in order to save the return address. In order to save the return address to your code, but it will use a system stack to do it. So that's why you do not see the problem, because it is not using your stack. There are different stacks when you're dealing with a protected mode operating system. Windows is protected mode. Yep, go ahead.
Well, I was going to ask is, at the hardware level, is that still on the RAM, or does
Yep.
that?
Mm-hmm.
But
It's
just
the
a
same
special,
stack.
It's just a special space that the kernel deals with.
Correct. So in this case, so let's say we coincide this with the use of the actual stack. Okay, so this is the stack, and there's only one. Okay, remember we're dealing with a simple architecture that is capable of interrupting, but it only has one single stack. Okay, so at point 1, okay, so at point 1, this part of the stack belongs to Tech. Okay, it has got my return addresses, my parameters, and so on and so forth. Okay, however I choose to use the stack is still here. But after point 1, when we get to point 2, which is the execution of the ISR, I'm going to label this part green. The ISR will first push its return address here. So this is the return address to Tech's code. That's the first thing that this green arrow is going to do. So this green arrow is causing this return address to be pushed on stack, which is right below where the stack pointer was pointing to. Okay, and then whatever it has to do with 2 and 3, so with 2 and 3, it can now consume additional stuff on the stack. In other words, when the ISR executes, it can consume an undisclosed amount of stack, and I have no idea exactly how much. Is that okay? So that entire green area on the stack is now overwritten by the ISR. When we have the transition back to my code, which is the green, which is the red arrow here, let's label this one 4. Okay. So when 4 happens, what it is doing is actually using the return address it's using the return address so that we can now resume execution in my code over here. So the stack pointer goes back to wherever it was before my code got interrupted. So from my perspective, nothing got changed. The stack pointer is now back to exactly where it was before the interrupt, and the actual program counter is now continuing from the instruction that got the last instruction that I executed before the interrupt. So as far as my code is concerned, it is just continuing just normal. I did not even detect, I could not possibly detect that an interrupt just occurred. Unless the interrupt has side effects to change some of the RAM locations, then I can check the RAM location and say, hey, did something happen over there? But without that, I would have no idea that an interrupt happened. Okay. Yep, go ahead.
So given that protected mode exists and those values are protected, is what we're doing mostly convention, or if the operating system protects those values but if the stack pointer get changed?
The operating system protects your stack by having its own stack. So when interrupt happens, the first thing it does is it will change the privilege level to the highest possible one before it executes the ISR. Because the ISR will definitely need to access input-output locations and talk to your SATA controller, talk to your USB controller, talk to your graphics card, and so on. And to do that, it needs elevated privilege levels. So there's a lot more happening when we're dealing with a protected mode operating system. But one of the side effects is it's not going to use your stack.
So my question is, if that's the case, why do we have to worry about it? Why not just...
Because when you write code, especially in assembly, your machine may not be in protected mode at that point. That's one. And two, if you're writing low-level kernel code, then you don't have the same protection anymore, because your code is already running at the system level. So when interrupt happens, it's using your stack.
Gotcha.
Because you are already the kernel. So when interrupt happens, it's already using your stack. So by practicing by using this kind of safe way of using the stack, you would not develop a habit of, oh, let's just use whatever space we have on the stack. Okay?
Gotcha.
But there's also another kind of pragmatic and kind of interesting reason why we want to kind of emphasize this. Okay. Arduino. Okay, Arduino. Okay, it's typo. All right, so how many people know what is an Arduino? Any version, doesn't matter which one. Some of you don't. Okay, so the Arduino is basically a small little circuit board. Let me see if I can find a picture. Yeah, there we go. So this is the smallest, probably one of all the Arduinos, but it's kind of interesting because it is inexpensive, and you can write C programs on it. Okay. So we'll click on it because I want to know how much it is. 21 bucks. Okay, and you can probably find it even less expensive somewhere else, I would suspect.
Chinese version.
So right here we got 20 bucks, 26, huh?
It's a different one. It's a drop down one.
And DigiKey usually has really good prices, especially when you order in quantities. So we can check out the prices here. Doesn't spell out how much. These are the daughter boards. Does it have pricing? Oh, right there.
On the right.
Yeah, extended pricing is 25 bucks ish. So it's about 25 bucks, okay? But when you look at the components, it's not really that expensive. So you can actually put something together like that, in terms of having the components, and then you use the tool to program. So the Arduino tool is a C++, type of programming tool. And so it seems like, hey, I can do the same kind of programming as I can do on a PC. Well, not quite, because it doesn't have an operating system. It doesn't even have protected mode operation. So you can no longer assume that when interrupts happen, nothing is going to happen to your stack, because there's only one stack, and it is your stack. When interrupts happen, it's using your stack. Okay? What kind of interrupts are we talking about? This is an embedded processor. Do we really have to worry about interrupts when we're dealing with a processor like this? Okay, so it uses a particular processor. I don't know which processor it uses now. Ooh, this one actually uses a ARM Cortex processor. So it's a 32-bit operating system. I did not know that they move on to the ARM processor. But it has a lot of components. So what do you do with an Arduino? For those of you who have an Arduino, yeah, go ahead.
You write very basic input-output instructions.
It can be very basic, but it can also go as complex as using Ethernet. So you can have your tiny micro nano web server implemented with 21 bucks, 25 bucks. Okay? So when you're dealing with networking, and at the same time it needs to maintain like temperature and monitor this and deal with that and so on and so forth, do you think interrupts can happen? Your Ethernet controller will say, okay, we just received a packet, go process this. Okay? And then at the same time, your motion detector may detect something and say, hey, there's something happening here, I detect motion, what should I do? The main processor chip can also talk to peripheral chips, other chips, like the compass, like motor controllers and whatnot. And all of those other chips can from time to time, ask the processor and go like, hey, you asked me that if this value is beyond this range, tell you about it. I'm interrupting to let you know that just happened. Okay? So all of those things are going to happen when you're writing your C code, right? Do you think your stack, below the stack pointer can get corrupted? Well, not corrupted, but clobbered, overwritten. Okay? The idea is yes. Okay? Absolutely. So when you write code using these embedded controllers that has no operating system and is not running in protected mode, what we just talked about is 100% relevant. Is that making any sense? Go ahead.
Is there any way to make a second stack within your primary stack or the only stack?
Yes. So when you're dealing with, okay, so what you're talking about is related to multi-threading. So in multi-threading, one thread has its own, every thread has its own stack. But when interrupts happen, if it's not in protected mode, the interrupt will just use whatever, it will use the stack of whatever thread is active at that time.
But that probably isn't a multi-threaded processor. That might just have one thread, right?
The processor itself is not multi-threaded, but it is the kernel. It's a multi-threading kernel that makes it multi-threading capable. In other words, multi-threading on a processor like this is more of a pretense than anything else. It's an illusion. Okay, so you can basically say, you have a few functions. Okay, so what multi-threading is in the same program. You got function f, you got function g, you got function h. Okay, so you write these functions just normally. So in multi-threading, what it means is you can call a system call to start a thread with function f. You can start another thread with function g, you can start another thread with function h. What that means is the system, either you or the system will allocate a stack to run that thread that starts with function f. Another stack is going to be allocated to run function g. Another thread is going to be allocated for function h to run function h. But they're being run quote-unquote simultaneously or concurrently. Your processor can have a single core, can have a single ALU, can have a single whatever. It's the multi-threading kernel that is giving you the illusion that these three functions are all operating at exactly the same time.
Right, but
Yep.
when those functions cease to be used, when they finish their operation, they're deallocated, right? Their stack is...
Well, when they're done operating, then it depends on your main or whatever main thread is remaining to determine what to do. I mean, usually the stack is no more than an area in RAM that you have control over of how to use it. So you can use it for whatever purpose you want to use it for.
Well, but what I'm trying to figure out is whether or not you could dedicate a space in the stack for interrupts only.
No,
That is in the
because that is a hardware issue.
Oh,
Because if you want interrupts to have its own stack, then the processor in the hardware has to have the proper gates and the logic to do it. And I don't know of any processor that has the ability to say, this is your interrupt stack, do not bother the other threads. I just don't know.
That'd be a software level of versus, like you said, hardware level.
That would be a hardware solution, but I'm not aware of any processor with that separate stack just for interrupts. So is this discussion going okay? I mean, are we kind of understanding why we have to why it is a big deal whether we access below what the stack pointer points to. Okay, cool. And what do we people use these things for? If you look at the size of this thing, it's kind of small. And let me see if I can find technical information. Well, let me find out. Okay, I can tell you what the size is because these pins, okay, let me see if I can get, bigger picture is good. So these pins are typically spaced what we call 100 mil, which is 0.1 of an inch. So we are looking at, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's about an inch. So the entire thing is approximately, I'm just guesstimating here, it's about 2 inches by 1 inch, which is not very big, okay? Power-wise, it is not using a lot of power. These things, at 5 volts, I'm gonna assume it's gonna be using maybe 20 milliamps or so, which is not a whole lot, okay? It's a very small amount of energy to keep it running. Weight-wise, you're talking about a circuit board that has no particularly heavy components, and it's only about this big. So it's not going to be that heavy, which makes it possible to, if you know how to use it, it's not a big deal in terms of physically being able to carry it onto an aerial drone. So what would be one of the things that you can use these things for on a drone? Flying drone, by the way.
Everything the drone needs to do. Set it up with a
navigation.
You can set it up with a camera processing.
You can do it with camera processing.
We need an external storage for the information, but
you can hook it up to GPS, right? You can hook this up to a GPS unit, which will then allow your drone to be at least in some aspect autonomous. You can set up a route, okay, and the processor can just will use the GPS feedback to control its flight pattern in order to fly in a particular way.
There was a geocache box that someone made using an Arduino that would only unlock if you went to the specific location that was set, inside of it.
Mm-hmm.
So
or in a particular order.
Yeah,
you might have geocache boxes, that you have to traverse in a particular order for those to open up. Yep.
So I just have another question. So when you're dealing with these types of devices, is this more of a computer engineering embedded systems type of? Like,
that's a very good question. The design of something like this is computer engineering. But once you have it done, the programming of this would still be somewhat computers. That would be kind of like a hybrid between computer science and computer engineering. Because the code that goes onto these things is separated into usually 2 parts. One part is what we call a device driver, and the other part is the application itself. The application itself is probably more computer science, but the device driver is more computer engineering. Because what the device driver is providing an API or an application programming interface to everybody who wants to use the device. So you provide an API and go like, okay, call this function or call this method of this object, and it will tell you what is the current heading bearing in degrees. Okay, so then 360 degrees, 0 is north, and so on. That's the API. So the rest of the program, which is mostly computer science people doing the programming, will just call this method of this object and say, okay, what is my current heading direction? Okay, 40 degrees, 50 degrees, or whatnot. But underneath the chip that is implementing the compass may not give you these things. It may be interrupt driven. In other words, it might take time in order for that chip to figure out its current heading. So the driver will need to say this. Okay, the driver will say, okay, compass, chipset, start, computing your current heading. But it might take like 50 milliseconds to do that computation. And it's not okay to lock up the processor for 50 milliseconds just to ask, compass, are you done? Compass, are you done? Compass, are you done? Compass, are you done? Because within those 15 milliseconds, your processor could have executed millions of instructions. So you wasted a lot of cycles. So what you do is you tell the compass chipset, they go like, start the conversion right now. When you're done, let me know. I'm gonna go back and do some more processing somewhere else. So when the compass chipset is all done, it will interrupt the processor and go like, hey, you asked me to compute the current heading, I'm done. But that heading may not be in 360 degrees because it doesn't make sense. Okay, it makes a lot more sense for the chipset just to tell you about the magnetic flux strength and give you a range of numbers that is a power of 2. 1023 is the max on this axis and on this axis. So your driver code is now going to the chipset and say, okay, I know your conversion is done. Tell me about the magnetic flux strength in 3D. Usually now it's 3D so that your device can tilt and rotate in any direction and it will still be able to give you the direction. So you will have to take that, you have to take the accelerometer reading and then do the cross product stuff with the magnetic flux in order to find out the true heading direction of the chip. And then you store that into a variable with an object so that when the API is called, you're just pulling a number that is already pre-computed. So the device driver side, which is the interrupt stuff, how to handle the interrupts, the ISR and stuff like that, that's more computer engineering than it is computer science, but it's an overlap between the two. So you might have someone who has a degree in computer science, or you might have someone who has a degree in computer engineering doing that part. But that's a very good question.
You focused on computer science.
My degree is in computer science, but my work, when I was a graduate student, the 8 years before I got this teaching job, is more of a computer engineer kind of job. So I can actually design boards like that. Yeah.
Do you?
Yeah, I do.
Can, I'm not sure if you still do it.
Yeah, well, I haven't done it for several years, but that was one of the projects that I did over a summer.
Oh.
Yep. But this kind of stuff is kind of interesting because we are now at a time in computer science where these things are getting inexpensive. $25, okay, that's not a whole lot of money. But it has 32-bit processor. It doesn't quite say it's a 32-bit processor. It doesn't quite say what is the clock speed, like how much processing power it has, but it's probably significant to do a lot of complex stuff. The significance is now you can say, okay, depending on how you hook this board up to, now we can do a variety of things. Tell me something that you think you might want to do.
Calculator.
A calculator? Well, you can do a calculator with this, but it's an embedded processor, which means it is typically put into a device that has no quote-unquote user interfaces. A calculator kind of have a user interface. Robotics, okay, that's a big one. Okay, what kind of robotics? Think of stuff that would be nice to automate, but may not be fully automated yet. Lawn mowing. Okay, dyslexic. Okay, lawn mowing. Yep.
I saw a cool project for it where a guy hooked it up to his coffee maker, so he automated coffee every morning for himself. He had one of the old school ones that you could program.
Okay. So you can automate a device that is previously not, doesn't have the ability to wake up by itself and to do stuff like that.
It uses an internal clock.
I think so.
Then you have to change it for daylight savings.
But we got applications. But we got applications that are already in place. You can buy robotic vacuum cleaners.
Like the Roomba.
Like a Roomba, exactly. That's I mean, if you think about a Roomba, it definitely has a processor inside. Okay.
Oh.
If you go to downtown, I think it's the Chavez park. They have automated lawn mowers. I observed one. It's really kind of interesting. So it will do the lawn mowing, and then when the battery is depleted, it knows how to get back to the charge station by itself, plug it in, and then charge, and then I guess after charging for X amount of time, or when the battery is back up to a certain point, it will go back out and continue its mowing. That would be impossible without something like this.
How big is it?
The lawnmower?
Yeah.
It's not that big.
Really?
I would say it's about yay big.
Really?
Yeah, it's electric too.
I'm just surprised they're
silent.
Trust no one to like mess with it or knock it over or something.
Well, the processor probably has temper, protection, so when somebody is really trying to mess around with it, it can send out a signal, and then you can alert people who are actually working in the park, and it can disclose its current location, right?
It's a giant outdoor robot.
Yeah.
I assume it probably yell, anyone that touches it, just like the car alarms, they get too close.
Think of the application from SMUT's perspective, okay? To think of all the transmission lines, okay? So right now, they don't have any way to really keep an eye on all the transmission lines because it's expensive to fly helicopters, all the way out. But if you have drones, they are at least, semi-automated, which means, they're pre-programmed to go to specific spots and, use, visual analyzing or visual analysis to look at the transmission lines and look for problems. And also with the transformers, the transformers that how many people live in a house or apartment where the transformer is above ground and you can actually see it on a post or something like that? Those things do fail, okay? They mostly fail because the oil inside for cooling purposes will go bad over time, okay? Or somebody takes a pellet gun or 22 rimfire and shoot at the transformer, the oil leaks out and that thing is going to overheat and die, okay? But if you have embedded processors available, you just attach one of these things to monitor the temperature, and then when you have drones to fly over periodically, the drone can pick up all that signals, okay? This transformer is still good, that one's good. This one probably has 2 more leaks to go, might want to make a note of that, and then it can just automatically go. And you don't need Wi-Fi or 4G connection or anything like that on the transmission, on the transformers, because now you have a drone to go fly around to collect all that data. But can you just kind of imagine, just one step at a time, you automate one little thing, how many jobs we can displace over time? How many smart employees will no longer say, oh, I have a job to return to tomorrow. We don't need you anymore. We got the drones to do your job. But that is the future. This is why I mentioned this, because this enables the automation of stuff. Because it's small, it is inexpensive, and it can do a lot of processing. And it is C programmable. You don't have to learn a new programming language just to do this. It's just regular C and C++. So I'm pointing out possible futures for you guys to explore. Exactly. Because I hate to write those commercial or banking programs. That would kill me. Yep.
Do you know about the computers that were taught how to program?
Mm-mm.
It exists.
Okay.
I guess they taught them enough to be able to learn from the mistakes and be able to program.
This is what I watched over the weekend.
Yeah.
And I disagree with the 7.7 over 10 rating. I think it is for computer geeks. I think this one is easily 9 over 10 or 9.5 over 10. Yeah, it's a very good movie, interesting, especially with the mention of Sophia, last week.
When did you watch? I was telling you to watch that in the beginning of the semester.
Huh?
This is the movie I was telling you to watch in the beginning of the semester. When did you watch? You finally watched it?
The weekend.
Yeah, I finally
It's
watched it.
good, right?
It is very good.
It's sick. I love this movie.
It's very creepy. It's very,
dude,
very creepy.
The ending, I'm just like, oh.
Did you see her?
Yeah, there was actually an alternative ending.
Oh, really?
Yeah.
I'm gonna check that out.
Yeah.
That's
Well,
sick.
not on movie, but when they talked about it, there was an alternate way of ending that movie.
Oh, sick.
Yeah, but it's very interesting because you were just talking about a computer learning how to program itself. This one is interesting because it is way beyond the Turing test.
Oh, yeah.
This is about a machine, deceiving humans, but using human imitation to deceive a human to achieve his own goals.
Yeah, super cool
Yeah.
idea.
Yep.
But then, like, I was all into when he was like the means he used to gather the information for the chip or the computer.
Yeah,
To, like,
for the robot.
use was basically like spying on everybody through their
Yep.
phones and stuff.
Mhm.
And how like he was like the phone carriers couldn't accuse him of doing